my channel, and today I'm going to be talking about Lagrangian mechanics. Lagrangian mechanics is kind of like Newtonian mechanics. In Newtonian mechanics, we didn't cover the really small, like quantum mechanics, or the really big, like general relativity. We just covered medium-sized objects and everyday objects, like an apple falling from a tree. So that was Newtonian mechanics. Like that, we have Lagrangian mechanics. Lagrangian mechanics is kind of like Newtonian mechanics, but it uses different types of mathematics and essentially means the same thing, but it's much more easier. So in this video, I'm going to be talking about how this equation, which uses the Lagrangian, is related to F is equal to ma, Newton's second law. So let's begin. So we have F is equal to ma. So let's get a quick recap from this. F is just the force, m is the mass, and a is the acceleration. So this is just a description over here. And remember, since they're next to each other, this means at times. Okay, so force is equal to mass times acceleration. That is what F is equal to ma is. Now, we're going to essentially take this equation, do some arithmetic operations and a little bit of calculus over here, and we'll eventually get F is equal to ma. So let's begin. So we want to first know what the Lagrangian is, because that's what Lagrangian mechanics is based out of. And we will later learn that there's also something called Hamiltonian mechanics, but we're not going to be discussing that in this video. So the Lagrangian is equal to t minus v. Well, what are t and v? Well, t is just the kinetic energy. On the other hand, v is going to be the potential energy. Okay, so we're now just going to take from a simple system the values of these. So we know that the kinetic energy is just going to be 1/2 mv squared for this system that we're dealing with. It could vary sometimes. And we know that the potential energy is just mgy. So the kinetic energy is 1/2 mv squared, and the potential energy is mgy. And notice that g is 9.8 meters per second squared. And when we have minus g, this is minus 9.8 meters per second squared. And this is the acceleration. Now this term will become very useful when we are going to transform this equation into F is equal to ma. So now, let's just compute the arithmetic operations by just subtracting them. So we have 1/2 mv squared, and then we're going to subtract it, and then mgy. Okay, so 1/2 mv squared subtracted by mgy. So we're just saying the kinetic energy subtracted by the potential energy, and this is equal to the Lagrangian. Okay, so now how do we simplify this? Because we really can't simplify it. So let's first identify the common terms. And mass sometimes is technically quantity. G is also a quantity, it's a constant. Y is going to be the position, or like the distance from the ground or something. So y is going to be variable, and v is also going to be the velocity. So we have this equation over here. So L is equal to 1/2 mv squared minus mgy. And we want to make it simple so that when we compute this, it's going to be more simpler for us. So how are we going to do that? Well, we need a simple substitution. We're going to state that y is equal to x. So what does this mean? Well, by y equals to x, we're just substituting the y term into x. So this seems pretty simple. 1/2 mv squared minus mgx. Now, what are we going to do? Well, we have v squared over here, right? Well, we'll just take the v over here. And remember that in high order derivatives, if we just take the function, which is going to be position, when we take the first derivative, we're going to get the velocity. Second derivative, we're going to get the acceleration. And notice that we can denote it, the velocity, or a derivative of something, by writing a dot for each derivative. So this is velocity, acceleration is x double dot. Okay, so this seems logical, and it's in the terms of x, so we can substitute this again. So we can say that v is going to equal x dot, since that's the velocity. So we're going to get 1/2 mv squared into 1/2 x dot squared. Okay, now that we've taken the Lagrangian, actually put in the terms, then analyzed it, and then after that make some substitutions, and now we have a more logical but same result. So what we're going to do now is just plug this in for where the Lagrangian is, and then once we plug it in, we can solve it. So we're going to have partial L over partial x dot. So we're saying that we're going to take the partial derivative, so partial derivative of the Lagrangian, which is 1/2 mx dot squared subtracted by mgx all over partial x dot. So we're taking it with respect to x dot. And notice that we have an x dot term over here. So all we're just going to do is compute this, and this is very easy. So we know that since we have x dot, and if we treat, so let's just take this term and say that we're going to have 1/2, let's say we have z, 1/2 mz squared. How would we compute the partial derivative of this? Well, we would just take the 2, multiply it, so we're going to have mz, right? Yeah, so we're going to have mz. Kind of like that, we can just treat mx dot, 1/2 mx dot squared, kind of like this. So essentially, we're just going to get mx dot for this term, because we know that this term doesn't have any x dots, so it will cancel out. And this term, since it has an x dot, it has a power, we multiply that, these 1/2, the 1/2 and the 2 cancel, so we'll just have mx dot. So this is just going to equal to mx dot, and we know that. Now, we can plug this into the equation. The derivative with respect to time of mx dot minus the partial L over partial x. Now notice that it's not x dot, which we're taking with respect to. We're taking the partial derivative of the Lagrangian with respect to x. So let's do this. So we're going to have 1/2 mx dot squared minus mgy is equal to L. Okay, so we've taken the partial derivative of the Lagrangian with respect to x dot. Now we're just going to take it with respect to x. And remember that this is going to be an x. Okay, so mgx instead of mgy. Now, if we're going to take the partial derivative with respect to x, this term will cancel out, since we just have an x dot. So we're just left with minus mgx is equal to the Lagrangian. But we've taken the derivative of this, so we just need to take the partial derivative of this. Well, the x will cancel, and we'll just have minus mg, since we're treating the other variables or other constants and variables as a constant. So we're treating the other variables as a constant. So in partial differentiation, what we're doing is, instead of treating every variable as a variable, we're treating the other variables that we're not taking with respect to those as constants. So say we're going to take the partial derivative with respect to x of x, y, z. So we know that we have 3 variables over here. In implicit differentiation, we know that these are 3 variables, but in partial differentiation, we say that y and z are going to be constants. So what's the derivative of x? 1, so y, z will be the answer. So kind of like that, when we take the partial derivative of this, we're just going to get minus mg, right? Yes, so we're going to get minus mg. So now we can plug this into the equation. The derivative of mx dot minus mg is going to equal 0. Now, we can simplify this so it can be the derivative of, so this is t, of mx dot plus mg equals 0. So now that we have this simple equation that doesn't look with this all complicated terms, so it's very simple. We just have to take the derivative. And when we take the derivative, this x dot will become x double dot. So we're going to have mx double dot plus mg is equal to 0. Now, this is where we kind of have the relationship of f is equal to ma with the Lagrangian. Okay, so how are we going to have the relationship? Well, if we think about it, we know that g is, and minus g specifically, is going to be the acceleration, right? So what are we going to do? Well, subtract that. And we subtract that, we're going to get essentially over here mx double dot is going to equal to minus mg. Now, this looks like a ratio or a proportionality, but we know something over here. So we can say we'll just divide by the m's. If we divide by the m's, we'll get x double dot is equal to minus g. We know that minus g is the acceleration, so we know that x double dot is going to be the acceleration too. But what's some other things that can help say that x double dot is the acceleration? Well, over here we have position is going to be our essentially variable, and then once we take the derivative of that, we're going to get the velocity. If we take the derivative of that twice, we're going to get the acceleration. And remember that I denoted that x double dot is going to be the acceleration, which means that we're going to have the mass times the acceleration is equal to the mass times the acceleration. So remember that minus g is going to be the acceleration, which is why we have the minus sign. So what can we do now? Well, we can set mx double dot equal to the f, which is the force. And we're just going to get f is equal to minus mg. Now, we know that this is just going to be the acceleration, so we can say that f is equal to m times minus g. Well, minus g is just a, so we're going to have f is equal to ma. And that is how we're going to get f is equal to ma from this big equation. So just to review what we did, we had this big equation. The derivative with respect to t of the partial derivative of the Lagrangian with respect to x dot, all of that which I just said, subtracted by the partial derivative of the Lagrangian with respect to x is equal to 0. So what do we do first? Well, for the system which we're analyzing, we knew the kinetic energy and the potential energy. So the kinetic energy is T, potential energy is V, and we know that the Lagrangian is the kinetic energy subtracted by the potential energy, and we know that the kinetic energy is 1/2 mv squared. And if we subtract that by mgy, which is the potential energy, we get the Lagrangian. Now, since we have different variables and a lot of different complicated things, what we did is we substituted y is equal to x. So y, which is the position, is going to equal to the x. So y the position, so y is the position, now x is the position. And we know that velocity is the derivative of position. So now we could write the two of the important terms in the form of x. So we're going to have 1/2 mx dot squared minus mgx. Now that we've gotten this into this form, we can actually take the partial derivative of the Lagrangian with respect to x dot. If we do, this term will cancel and we'll just get mx dot. So once we take the derivative with respect to t of mx dot, we get mx double dot. And then we're going to take the partial derivative of the Lagrangian with respect to x, which means we just get minus mg. So we have mx double dot subtracted by minus mg is equal to 0. Well, this is just mx double dot plus mg is going to equal to 0. We subtract mg from both sides, so we get mx double dot is equal to minus mg. And remember that we stated that minus g is the acceleration, and we have minus mg, which is just m times minus g. And we know that minus g is the acceleration, so we can state that m times a is equal to mx double dot. We also know that the x double dot is the acceleration because the twice derivative from the position will give us the acceleration, which we can denote as x double dot. Okay, so we've got this, and we said that mx double dot is going to equal to the force. And we have force is equal to mass times acceleration. And this is how F is equal to ma relates with this Lagrangian use of equation. So this equation, which uses the Lagrangian specifically, We can use this to state that the Newtonian mechanics and the Lagrangian mechanics are technically the same thing. If you like this video and if you like this channel, please subscribe to learn more. Thank you.